Right. The next speaker is Yue Wang from NVIDIA Research
at the USC.
And assistant professor.
Yeah, across the street.
I know.
Yeah.
No, thanks. Thanks for being here. And US working on, let's say, uh, data to train AI in robotics, and for instance, using non-robotic data for training of AI and robots. And he'll be speaking about scaling up robotic data with minimal supervision.
Yeah. Thank you so much for the introduction and the invitation. So, hello everyone. My name is Yue Wang, and today I'm going to share with you some of our recent works on how to scale up robot learning with with minimal human supervision. So, basically, in the past few years, we have been seeing a covering explosion of robotics. So nowadays, you can take a Waymo self-driving car in downtown San Francisco, LA, and Phoenix. And also, this Unitree humanoid robot can play very complicated motion. And also, you can use some high dexterous manipulators to perform many precision manipulation works. So what lead to this success? So to me, there are three important factors. The first one is hardware. So we have developed so many very good hardwares in the past few years. For example, this Unitree humanoid robot and sharper wave high dexterous hands, and also this animal quadruped robot. So just give you some examples. And also on the algorithm side, we have been developing many good deep learning AI algorithms to solve the intelligent problems for robotics. For example, this diffusion policy developed by Shuan's lab has been used for many imitation learning works. And also we now have vision language action models, which is fine-tuned VLM to perform some generalizable manipulation or general robotic tasks. And also what is even more important is now we have ways to collect data and to train algorithms from our daily collect data. So for example, we have this NVIDIA's SX simulation, and also we have some tools to collect real world data from with human labelers. So to me, data is probably the most important factor, and today I'm going to focus on the data aspect of the robot learning development. Why is that? So to me, data is probably the key to artificial intelligence. If we take a look at the trajectory of computer vision or AI in general in the past few years, we will realize data is probably the most important driving force. So for example, before deep learning, if you are a computer vision or robotic perception researcher, if you want to develop some perception algorithms, so you will probably use some hand-designed feature descriptors such as HOG or SIFT combined with SVM to perform a visual recognition task. And then with development of a large data set, such as ImageNet, we have more powerful models, such as convolutional neural networks. So now we can use convolutional neural networks to tackle even more visual recognition tasks, including classification, object detection, semantic segmentation, or other general perception tasks. And after that, people develop transformers, which is a more powerful neural network architecture, and of course, it's more data hungry. But people also develop a way to collect data from the whole internet so that we can train the transformer model using internet scale data. And very recently, people developed vision language models that is trained on multi-model data. So you have an image and also have the description for the image. Now you can basically train a multi-model vision language model using this multi-model data to solve many general domain and open vocabulary visual recognition tasks. And this is basically, for example, GPT-4o or other state-of-art foundation models. And of course, the next stage is how can we use these powerful models to solve physical AI problems? So can we develop an even more powerful model using large data to solve some robotic problems? collecting robotic data is much more challenging, as you can imagine. So let's make a comparison between this image annotation task and this robotic data collection task. So on the left is a tool for image search and annotation. So basically annotating this data, annotating a single image takes less than 1 second. And also we can do this all over the world. So meaning that the data cost per sample per example is probably just 1 cent. So it's pretty cheap. However, if we look at this robotic data collection pipeline on the right, so by the way, this is developed by colleagues from Berkeley. It's called the Jello system. So you have these two manipulators, and also you have a ladder to control these two manipulators. So what people do is use this teleoperation system to collect some real-world demonstrations. However, capturing one single example takes more than 60 seconds. And also this is confined to lab environments. If you don't have a robot, you cannot collect data. So the data cost per example is about $5. So as you can see, this is much more expensive than capturing or annotating image data. And of course, for space robots, their collection is even more challenging because there's no way that we can access the environment and we can access the space robots. So how can we address the data issue? So my lab have been developing algorithm to solve this single problem. So can we convert a single image into a robotic data? So can we download the images from the internet and then somehow we convert them into some robotic ready data so that we can train our physical AI algorithms on? So this is a image we download from the internet on the left, and our goal is basically to convert it into a robotic ready data, and we want to put some demonstrations into the data, and also we want to reconstruct 3D information from this single image so that we can generate data from multiple views. So this is a goal of my lab. And next, I'm going to share with you some of our recent works that we did in the we did to generate data or augment real-world data captures. So let's use this autonomous driving scenario as an example. So this is a video captured by an onboard sensor autonomous vehicle. And what we want to do is we want to basically reconstruct 3D information from this video, and then after that we can render some novel data from new viewpoints so that we can basically generate new data. And this paper is called the Omni Urban Scene Reconstruction that is led by my student Ziyu. And essentially what we want to do is we need a way to first reconstruct this 3D information from this video. Before that, we need a way to represent this 3D scene. So the way we represent this 3D scene is called 3D Gaussian Splatting. So what is that? So basically, 3D Gaussian splatting is has two parts. The first part is you want to represent the 3D scene with some primitives. So the primitive we selected is basically as simple as a Gaussian, right? So for each Gaussian, we have 4 sets of parameters: position, where it's located, and the covariance, how the Gaussian is stretched. And also we have a color associated with each Gaussian. Also, we have parameter to see the transparency of each Gaussian. Of course, with a single Gaussian, you cannot represent this very complicated scene. But what if you have multiple Gaussians? Assuming you have, let's see, millions of Gaussians, then you have a way to represent this 3D scene with this ensemble of all the Gaussian primitives. So that is how we basically represent the scene. And the next, we need a way to basically tackle or model different actors or agents in the scene. As you see, this scene has many different categories. For example, it has cars, moving pedestrians, background, etc. We need a way to decompose this thing into different categories, and for each category, we use a set of Gaussians to model them, because essentially there are different objects. For example, the pedestrians are deformable and the cars are rigid, so we cannot use the same Gaussian representations to represent them. So how can we do so how can we classify this thing into different categories? So basically what we do is we represent street and sky as a background. So they are always static. So it's very easy to model them. And we also model some rigid objects such as cars, buses, because as long as we know their rigid transformation, we can just treat them as the static objects. We can model them in their own coordinate system. So the challenging part is moving pedestrians because they are deformable objects. But fortunately, researchers from computer graphics community developed a model called simple model, which is a template model to model human body. So we can use this simple model to represent different human bodies with a small set of parameters, of course, combined with our Gaussian representations. And also we have other objects that cannot be modeled by this simple model. For example, some cyclists, because they are attached to the other object, we do not have a general parameterized model to represent them. So that we just use what we call deformable Gaussians to represent any of the distribution, any out of category objects, such as a cyclist or people on wheelchair, etc. And after we do this classification, we need a way to bring them back into the 3D space. What we do is we construct a scene graph to basically connect all different categories so that when we generate novel or new observations from a new view angle, we need to reason about their collision, etc. So if we generate this Gaussian scene graph, we can just work through this scene graph to reason about like the collision information, etc. And then we can basically put all the different objects back into the 3D scene and render from a novel view. Of course, I skip all the details because of the time limit. We can, if you are interested, we can talk about some details after that. So let's look at some applications we can enable. So the first application we can enable is scene editing. So as you see, we capture some driving scenarios, and then we can basically add some animations. We can add some new characters into the scene to simulate novel observations so that we can train our algorithms with this auto distribution data. And second application is we can generate a new driving scenarios. For example, in the first row is the reconstructed scene. So this red car just cross the street, right? Because there's no pedestrian, etc. However, in the second scene, we can basically simulate a pedestrian passing the street and the red car to stop at the pedestrian. So we can generate this novel driving scenario because in the real world, capturing such scenario, so first it's very rare and also it's very dangerous. But we can simulate this scenario with this Gaussian-based reconstruction model. And also we can do some super slow motion to generate some new data or auto distribution data for algorithm training. And that was our work on how to use reconstruction, Gaussian splatting-based reconstruction to tackle robotic data generation. So next, I will switch gear and to talk about how we learn from pure non-robotic data for robot learning. So essentially, what we want to do is we want to manipulate unseen objects in unseen environments with unseen environments. So think about we have a robot, and when we deploy it into the real world, we do not want the users to capture data and retrain the algorithm. We just want the robot just work for any new scenario off the shelf. So we basically tackle the generalization problem. And we don't want to capture any cost expensive in-domain data by the users. So we want to basically leverage abundant out-of-domain data, internet data, to learn some versatile manipulation capabilities. So we have many different out-of-domain examples. For example, we have this human object interaction data from the internet. We have this Tom and Jerry animation, and we have AI generated images. So how can we leverage this abundant out-of-domain data for robot learning? So we have this work called RAM, retrieval-based affordance transfer for generalizable zero-shot robotic manipulation. That is done by my student Yu. And essentially, the key to leverage different out-of-domain data is to represent the actionable knowledge original in the data as transferable affordance. So what do I mean by affordance? So if we think about a simple manipulation task, if we want to open the drawer, so the simplest information you need is basically where to act. So you need to know where the 3D contact point is, and also how to act, what the poster contact direction is. So as long as you know these two types of information, you can basically use off-the-shelf motion planning to execute to finish the task. So that is basically the high-level motivation of this work. So we basically want to represent the actionable knowledge as simple as what we call the transferable affordance. And once you have this transferable affordance, you have a database of all the auto domain data. And when you tackle a new task, you can just transfer the affordance from your source domain, from your database to the new data. However, the problem is, how can you transfer the affordance? How can you match data with different appearance, geometry, etc.?
Yue, are you watching the time?
Oh, sorry. Yeah, I will quickly finish this. Yeah, so basically but fortunately we have these vision foundation models to tackle this issue. So we recently people developed very powerful feature matching tools by vision foundation models to match these different folders. And I will skip all the details very quickly. So maybe I should jump to the applications of this work. Yeah, so basically, with this very powerful affordance representation, we can tackle many different manipulation tasks in a zero-shot manner. So, for example, we have this open the microwave task, and we don't need any in-domain demonstrations by the users. So what we do is we just retrieve a demonstration from the internet, which is shown on the top right, and then we can transfer the demonstration to the target task and finish the task. We have other demonstrations. And this is a pickup and place task. What is very interesting is that we can learn manipulation from Tom and Jerry. So for example, if we have this cartoonish demonstration, we can even transfer the actionable knowledge from animation to the real world. And this is done purely zero shot. And then finally, I will quickly show you that with the same concept, we apply the same concept to humanoid robot learning. And we have this recent work called UH1, which is try to learn humanoid robotic manipulation skills from internet video. So what we do is we look at the internet and we download all the internet videos that with a single person motion, and then we transfer their motion from the human space to the humanoid space. Then we collect a very large data set for humanoid, and we transformer model for humanoid robotic control. And this is some demos that we show that we can basically give an instruction to the humanoid, which is on the top left, and the humanoid will basically play the motion. I will skip this. By the way, this is my student who led this work. Okay, with that, I want to thank all my students, collaborators, mentors. Without them, these projects can be possible. And I also want to thank all the funding agents to support our work. And also, thank you so much for listening. And I'm happy to take questions if there is time.
Thanks a lot. Yeah, let's do one quick question.
How your model reacts if you say what would happen and there is enough happening.
That's a good question. So we probably, you mean like for the target task, we don't have any cabinet, right? Yeah, because we have a high-level language model controller, and the high-level the language model controller basically can do some reasoning and see there's no cabinet, etc.
So you can just not do anything?
Yeah.
That's right.